Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. So let's continue chapter 9. So we stopped at this problem. Let me just remind you of this problem. We have a collision, could be elastic, could be inelastic. The first object is moving, the second object is stationary, and then they collide. I gave you the masses, and I gave you V1, the velocity of the first object. The velocity of the second object is stationary. And then I gave you the velocity of the second object after the collision. I ask you what is the velocity of the first object after the collision. And we said momentum is conserved in the x-axis, and based on that we find the x component of V1 prime. Now let's find the y component of V1 prime. So we write let me change the color just for fun. Physics is fun. In the y-axis we have Py before the collision must equal Py after the collision. So that means M1 V1y plus M2 V2y must equal M1 V1y after the collision, prime means after, plus M2 V2y prime. Now pay attention to this, and we assume that V2 is equal 0. We can have a component for V2, but just to make things much easier. So in the y-axis V1 was a component of V1 in the y-axis was 0. Component of M2 in the y-axis is 0 also. So the total momentum before the collision was 0. So after the collision, I know the component in the y-axis for the second object. For the first object, 1.5 V1y prime plus the mass of the second object multiply minus 1.07. So I put the number 0 is equal 1.5 V1y prime plus minus, so it's a minus 0.535, and that will lead to V1 prime is equal 0.535 over 1.5, and that is 0.36 meter per second. It's a positive component. Finally, V1 prime as a vector has two components, 1.15 I plus 0.36 J meter per second. Any question? Yeah, if L2 change, then the momentum here, you will have a component. You'll have a component here. V2y, you have a component. And if it change in the x-axis, you'll have here a component for V2. Of course, now you can get theta. This is another way of asking to find the vector after the collision, V1 after the collision, because from the y component and x component, of course, I can get theta. Well, we go to the basic. If you are asking for theta, well, this is V1 vector. This is theta. This is Vx. And this is Vy. So then V1 cosine theta is equal to Vx, and V1 sine theta is equal to Vy, or sine over cosine theta tan theta is equal to Vy over Vx, whatever you like. طيب عادل is هون? Is he here?
Yes, I'm here.
يلا اتحفنا يا عادل. Read it for us.
Okay. So, an 1800 kilograms car stopped at a traffic light is struck from the rear by a 900 kilogram car. The two cars become entangled, moving along the same path as that of the originally moving car. Smaller car were moving at 20 meters per second. The collision. What is the velocity of the entangled cars after the collision?
طيب شكرا يا عادل. So first of all, he told us become entangled. So right away it's a total inelastic collision. We call it total inelastic collision because they stuck together, they entangled. So let's write the information given for us. M1 is equal 1800 kilogram. M2 is equal 900 kilogram. V1 was 0. Again, momentum is a vector. However, if we deal with it in one dimension, then plus and minus will deal with the direction of that vector. V2 is 20 meter per second. He asked us what will be V after the collision when they stuck together. So in this situation, the collision is internal between the two cars, so no external force. So change of momentum must equal to 0, and that means P final total momentum final must equal total momentum initial. Let's apply it. So what's the total momentum final? Well, now they are one object, so M1 plus M2 V final must equal to 1800 multiplied by 0 plus 900 multiplied by 20. be careful here. The car is 0, so the sign is not important. However, if the car is moving forward, then it's a positive. Or if the car, for example, going in reverse, it's a negative. We are dealing with vectors here, but in one dimension, so be careful. So we just put the number, so v prime will be equal 6.67 meter per second. So both cars, after the collision, will go forward at this amount of speed, or velocity in one dimension is positive velocity. So it will, both cars will go in the same direction of the second car. And I think this is very, very easy. The easiest question you can get. طيب. يلا يا عادل, read for us.
Okay. The ballistic pendulum apparatus used to measure the speed of a fast-moving projectile, such as a bullet. A projectile of mass m1 is fired into a large block of wood of mass m2, suspended from some light wires. The projectile embeds into the block, and the entire system swings through a high edge. How can we determine the speed of a projectile from the measurement of edge?
Okay. So this situation is a practical situation, like it is used in real life. It is used in real life. And if you search the net, مثلا, or somebody is interested, you will find that each gun or each rifle is rated. They tell you that the speed of the bullet for Kalashnikov, for example, is this amount. The speed of the bullet of M16 is this amount. The speed of this gun is this amount. How we measure it? Well, by this experiment, by ballistic pendulum, called ballistic pendulum. Basically, we have some mass. It is handled freely to move, and then we shoot the bullet directly on that mass. So it will be embedded after, and as a result, the whole block and the bullet will move in a pendulum motion. Well, in that pendulum motion, kinetic energy is converted into potential energy. So in the second part of this problem, mechanical energy is concerned. In the first part of this problem, kinetic energy is not concerned. So when they collide with each other, kinetic energy is lost, or part of the kinetic energy is lost. However, when the bullet is inside the wood block, now mechanical energy is conserved. So whatever kinetic energy the wood and the block have will be transferred into potential energy. So let's try to solve it. I will give you hypothetical numbers. I brought it from the internet, and let's see what's a real situation will be. So from the internet, for a Kalashnikov, for example, or AK-47, we have mass of the bullet is equal 7.9 grams. The speed, or velocity in one dimension of the bullet is 715 meter per second. Mass of the block, the big mass, is equal 3 kilogram. So here is 3 kilogram, for the bullet 7.9 gram, and for the speed or the velocity 715 I meter per second. And again, this is vector. We can ignore it in one dimension, and it will be a positive and negative will tell me the direction of that vector. So, as I told you, we have two parts in this problem. The first part, momentum is conserved. So let me use colors. So, first part, momentum is conserved. Kinetic energy is not conserved. So as a result, B total final must equal B total initial. And this is in one dimension, so I can get rid of the vector sign. What is B final? P final, momentum final. Well, it's mass of the bullet plus mass of the block, V prime, that's after the collision. Like, what is total momentum before the collision? Well, it is mass of the bullet multiplied by the speed of the bullet plus the big mass multiplied by V of the mass, which is a 0. So this is 0. Yes, block is stationary. We put the numbers. So V prime is equal over so let's put the numbers. So what will be V prime for both bullet and the block? Can somebody help? Anything? Nobody is helping. 18.34 watt. Sandwich, banana, orange, meter, centimeter. It's not 18.78, it's 1.88. Let me just double check my numbers. Be careful, this is 7.9 grams, not 97. Okay, so be careful here, يا جماعة. Seven point nine gram, and 7.9/1000, 0.0079. So it will be 1.88 meter per second. So now the block and the bullet are moving with a speed of 1.88 meter per second. So the second part of this problem mechanical energy applies like this. What's the meaning of that? معناته kinetic change in kinetic energy must equal change in potential energy. So now the bullet and the block are one object. So what is the change in kinetic energy for the bullet and the wood block? Well, final kinetic energy is 0. Initial kinetic energy is equal half m bullet plus capital M v prime square, and this must equal m plus n, that is mg h. So right away, both masses final kinetic energy, because it will stop. The block and the bullet will move in a pendulum motion, circular motion. So as it moves up, it will slow down until it stops. So final kinetic energy must equal to 0, because finally it will stop. So we are interested in H. We put the numbers, so half 1.88 square is equal 9.8 H. Yani H will be equal to 18 meter, 0.18 meter. Yani when we shoot the bullet on that ballistic, in this situation, ballistic is 3 kilogram, bullet is 7.9 grams, speed is 715. The height of the ballistic pendulum will be 18 centimeter. Also, another way of asking this, I will ask you what is the angle of the pendulum. What is the angle of the pendulum? So, in that situation, this is H, and this is theta. But to know the angle, I need to give you the length of the pendulum. But it can be done. We saw the problem like this before. Any question? تفضل.
Okay, so Doctor, basically, I get the concept here. Like we first use the momentum concept, then we use the mechanical energy concept.
صح.
And the future problems, how do I figure out this thing?
Well, depending on the type of the collision.
Okay, so
Depending on the type of...
yesterday we had, sorry, the day prior to yesterday we said there is 3 types of, or 2 types, like depending on our book, there are 2 types of collision.
That's correct.
And how to determine each on the other?
Well, if they stuck together, that's the second type, اللي هو total inelastic. If it does not stick together, the book decided to ignore the difference between elastic collision and inelastic collision. The difference between the two, if the kinetic energy is conserved, then you have elastic collision, and you have an equation that you can use اللي هو kinetic energy is conserved. So kinetic change in kinetic energy is 0.
Which is the case in this problem?
In this problem, no. In this problem, it's total inelastic collision. Kinetic energy is not conserved during the collision. However, after the collision, of course, mechanical energy is conserved.
Okay, so like you just said that before the collision, kinetic energy is not conserved.
That's correct, because they stuck together.
Can you give me like another example of when the kinetic energy is conserved? Like something.
Well, this problem that we just solved. This problem we just solved, it is an elastic collision.
Which means the kinetic energy is conserved.
Could be conserved. If it is conserved, it's elastic collision. If it's not conserved, it is inelastic collision.
And
Now, the book decided to ignore the difference between the two, because the difference between the two, when kinetic energy is conserved, you have a new equation to help you solve the problem. But then it's a different level of difficulty.
So do you mean that we don't have that equation?
No, it is there, but the book decided to ignore it. So I will not go into that level of difficulty. I have to stick to the level of difficulty of your book. But
so in other words, we won't be.
Yeah. So in other words, we will deal with elastic collision and total inelastic collision.
And we won't go nearby the kinetic.
As a concept, yes. As problems and equations, no. Not in this. Not in this syllabus.
Yeah, I got it. I was just confused.
That's correct. It is. Yeah. However, in other books, they will go into details that you have elastic collision, and you have 3 equations. Momentum is conserved in the x-axis, momentum is conserved in the y-axis, and kinetic energy is conserved. So you have 3 equations to write and use in your solution. If kinetic energy is not conserved, but it is still not sticking together, then you have 2 equations. Momentum is conserved in x, momentum is conserved in y.
And if we have 1 dimension, we only have 1 equation.
If you have 1 dimension, you have 1 equation. However, in total inelastic collision, when they stuck together, you have two equations. Momentum is conserved in x, momentum is conserved in y.
I have to mention.
Correct? So in this syllabus, we will deal with mathematically, يعني problem difficulty, we will deal with elastic collision or inelastic collision and total inelastic collision اللي هو they stick together after the collision.
Yeah, so the inelastic collision and the total inelastic collision, that's the problems we will be dealing with.
That's correct. However, in terms of principle, you need to know the difference between the three. When it is elastic collision, kinetic energy is conserved, momentum is conserved. When it is total inelastic collision, momentum is conserved, kinetic energy is not conserved.
All right, I got it now.
Fine. Any other question?
All clear.
Fine. Now let's move to a concept, very interesting concept, very important concept, اللي هو center of mass. Center of mass. هلا center of mass is very well known by humans, not by students in the university, by humans. يعني life trained you very well to deal with center of mass, to deal with center of mass. يعني I will tell you, for example, if I ask you to carry a ladder, سلم, yeah, what you will do, from where you are going to carry it? From the middle, correct? Well, based on the shape of the ladder, most probably you will carry it from the middle. Okay, did you take it in the class or life taught you? شايل السلم بالعربي. You see what I mean? It's life and it's telling us. Why? Because in real life, physics laws apply to the center of mass. Physics laws always apply to the center of mass. I will give you another example. يعني if you like to carry an infant, how do you carry an infant? You carry it from, carry him or her from the legs or from the head, or you carry an infant from the head? Yeah, you carry an infant, you put two hands around the center of mass and then you carry the infant. Yeah, so it's very well known concept to us before even we know that the name of that concept is center of mass. So that's an important thing, that already we know what is center of mass. Now, the first time we do the connection that what we are used to do and deal with life, you carry it from center of mass. Yeah, you carry it from center of mass. So it's a very well known concept. So here in our example, we will have two objects connected by a massless rod, so we ignore the mass of the rod, and masses are different. So if you push them in the first situation, if you push them above center of mass, they will rotate instead of moving in one dimension. If you push under the center of mass, it will also rotate. However, if you push to the center of mass, it will go into linear motion. It will go into a linear motion. هلا in most of physics problems, they will teach center of mass right after conservation of momentum. They will teach center of mass right after conservation of linear momentum. And to your surprise, center of mass concept is the legal son of conservation of linear momentum. Center of mass is a direct result for the conservation of linear momentum. Let me try to explain. So we start with large object and small object. They are not very different. Let me just exaggerate a little. And they are connected. So this is M2, and this is M1. And they are connected with a light object or the light rod, that it will not affect our result. So right away, from life experience, where will be the center of mass? Towards M1 or towards M2? Closer to M1 or closer to M2? From life experience. Forget that this is physics. So even if you ask any person in the road, he will tell you it will be closer to M2. So this is our center of mass. Even if it has a bigger density, we assume that mass 2 is larger than mass 1. So density does not apply now. Okay. So let's talk about one dimension. One dimension to get rid of the vector sign. Now suppose that M2 is moving with V2 and M1 is moving with V1. Let's write the equation of conservation of linear momentum. So if we look at the center of mass, so that now we are looking like nature. Nature, when it looks to those two objects, it will look as if it's just a total mass concentrated in the center of mass. It's like you, when you want to carry a ladder, you go to the center of mass and then you lift it. So as if the shape of the ladder is not important, it's just that you have a total mass concentrated in the center of mass. So then, what is the momentum of the center of mass? Like nature do. It is M1 plus M2, because I have the total mass of that two objects, and it is multiplied by the speed of the center of mass. And this is P total. But what is P total when you look at individual objects? Well, it is M1 V1 plus M2 V2. So when we apply the conservation of linear momentum, we will have M1 plus m2 multiplied by the center of mass speed must equal m1 v1 plus m2 v2. Well, ya Abdurrahman, v1 and v2 can be different because we can assume that this rod is just a spring. This rod is just a weightless spring. So V1 and V2 can be different. Not only like that, V1 and V2 can be opposite because those are vectors. Yeah, this object can move from right to left, and this object can move from left to right. If we have a spring, مثلا, they can. However, we are dealing here with vectors, so the sign is different, could be different, and magnitude also could be different. However, even if the magnitude of V1 and V2 are different, the sign are different, nature will deal with the center of mass velocity. Yeah, the connection between the two is rigid, or you can assume it's a spring. So for simplicity, it has no mass, so it will not affect about the center of mass. And the general case, the most general case, V2 is different than V1. How it's different? Could be opposite sign, could be different value. It's a general case. If it is rigid, no, it will not rotate. If we are moving in the positive x-axis, no, it will not rotate. Because the freedom of motion is only in the x-axis. So then, the conservation of linear momentum will dictate for us that the total mass, as nature look at it, it's the total mass multiplied by the speed of the center of mass must equal the momentum, the linear momentum of the first object plus the linear momentum of the second object. This is how we look at it, and this is how nature look at it. Because nature deal with the center of mass of objects. طيب, let's look at this trick in mathematics. What is V center of mass? What is V in general? It's the derivative of x with respect to time. To solve this problem, either you sum both momentums, or you look at the linear momentum of the center of mass. It's the same. It is the same. طيب, what is the speed or velocity? It's the derivative of x. It is the derivative of x. So let's apply it. So m1 plus m2 dx center of mass with respect to time is nothing but m1 dx1 with respect to time plus dx2 with respect to time. صح إيمان, شكرا يا إيمان. طيب, to get rid of the derivative, how about we integrate both sides? So we integrate this, and we integrate, let me just space, and we integrate all of this. So as a result, we have M1 plus M2 x center of mass must equal M1 x1 plus M2 x2. Well, the variable here is dt with respect to the time. So that means x, center of mass, the distance of the center of mass is equal m1 x1 plus m2 x2 over the total mass of the system. And this is how we get the equation of the center of mass. When and the equation of center of mass. Hi. Let me put them together. So this is the equation of center of mass. And it is direct result of the conservation of linear momentum. So when you apply conservation of linear momentum, right away you get the concept of center of mass. When you have dt, you have time on the right and on the left, so it will disappear. Exactly. Exactly. Adil said the same idea of how we derived half mv squared from the work. Exactly. Yes, integrating of in terms of time. So the center of mass. And by the way, I can also go from conservation of linear momentum to Newton's second law. Same derivation to Newton's second law. So in fact, Newton's second law is a direct result or direct consequence of the conservation of linear momentum. That's correct. In the book it doesn't say, I explain it here in detail just to see the relation. In other books they explain it. In other books they explain it that the center of mass is a direct result of the conservation of linear momentum. And it will help a lot, like from where we get the center of mass equation. Well, it is from the conservation of linear momentum. So it will help. طيب هلا how we apply this equation, يعني few notes of how we apply this equation. So we go back to our drawing. So this is M2 connected with M1, and we discover center of mass. It is here. So in order to put the numbers, we will deal with the numbers as a displacement, يعني as vectors. Sure, yeah, Ahmed. Yeah, sure. So we deal with x1 and x2, and the center of mass we deal with them as displacement, يعني vectors, يعني they have a sign. They have a sign. الحين where we put our axis when we solve such a problem, it does not matter. Does not matter. So, for example, I can put my axis here. And then this is x1, this is x2, and this is x center of mass. So here x1 is negative, x2 is positive, and x center of mass will be positive. طيب, suppose that, well, to make things easier, we choose our reference, so we can ignore one of the values. So either I put the axis on here or on M2. So what's the situation if I put my axis on M1? I will have x1 is equal to 0, x2 will be positive, and x center of mass will be positive. طيب, how about if I choose the axis on M2? Then x1 will be negative, x2 will be 0, and x center of mass will be negative. So usually in such a problem, we put the axis on one of the objects if you have two objects or three objects. So you put it on one of them, so to get rid of one of the variables. Or even if you put it in the middle, it won't make a difference because we are dealing with vectors here in one dimension. It's a displacement. So you have positive and you have negative. You know, the axis is whatever you like. It's just to find the center of mass from that axis. With respect, يعني the axis can be arbitrary, anything will work, but when we find the values of center of mass, it will be the difference between the center of mass and M2 will be always fixed. The distance between center of mass and M1 always will be fixed. Always, the distance is fixed. However, you assume any position for your axis, and it will give you the final same result in terms of how far center of mass from M2 and how far center of mass from M1. Always you will get the same result, no matter what axis you look at. طيب. So here it's just a generalization for this result. Here for two objects, M1 x1 plus M2 x2 over the total mass. If we have more than one object, M1 x1, M2 x2, M3, whatever, up to n objects, well, we just generalize our equation over the total mass, and here the center of mass in the X, and you have a center of mass in the Y, and you have a center of mass in the Z. So center of mass in the X is 1 over the total mass of the objects multiplied by the summation of each object from the origin, from the axis you choose. Same thing apply in the Y, and same thing apply to the Z. And of course, if you have X component for center of mass, Y component for center of mass, Z component for the center of mass, then you have a vector of the center of mass. So instead of dealing with one dimension, now we can deal with the center of mass as a vector in 3 dimensions. And we apply the same exact equation, the total mass of our particles, 1 over the total mass for our particles multiplied by the summation of each mass with its each r small vector. طيب, well, if we assume that we have so many particles in a system, yeah, it is confusing because I'm going when you go fast, but I'm going step by step. Is it confusing up to here? Up to here is not confusing, صح؟ لأنه we just prove it. Of course, so now this is the center of mass. Center of mass in the X, you have center of mass on the Y, and center of mass in the Z. It is the displacement, let's say, it is the displacement from the center, from the origin. It is the displacement from the origin, whatever origin you like. So you have the center of mass in the X, and you have a center of mass in the Y, and you have center of mass in the Z. So what's the meaning when you have X component and Y component and Z component? Well, then that means you have a vector, a 3-dimension vector. So we just apply the same exact equation and you end up with a vector. We just generalize what we get. Just generalizing X center of mass is equal M1 plus M2, X1 M1 plus X2 M2 plus etc. divided by M1 plus M2 plus etc. So we are just applying the same equation. And we said all those m's 1 over total mass, and then we have summation for mi xi. And basically we add X component plus Y component plus Z component, and we end up with an R for the center of mass. Okay. So now we assume that we have so many particles, and those so many particles are going smaller and smaller and smaller. So that means now the center of mass, X center of mass, is this equation 1 over M, X center of mass multiplied by a very small mass, and I is getting very large. So what we use this trick always when the number is very small and very large. So we take the limit and it's nothing but the integration. So x dm. So that means the center of mass, when you have an object, can be calculated by 1 over m, the total mass of the object, and then the integration of x dm. Same thing for the y and same thing for the z, and we apply it for the r. It is r center of mass when you are dealing with an object. We are not dealing now with many particles. Those many particles are, the number of those particles are going to infinity, and the mass is going to 0 or almost 0. So as a result, the summation is now transferred into integration. So we end up with this. No, we are not going. We are not going to practice. It's just a concept. Just a concept. However, in other books, yes, I will give you R. I will give you the vector R, and then you do a real integration with respect with m dm, and then you can calculate R. So in some other books, yes, you do calculation to calculate the center of mass of an object mathematically, but in our syllabus we just need to understand the concept of calculating the center of mass of an object. But you need to know that yes, if you have an object, you can calculate its center of mass by integrating the vector r with respect with m, with the mass. Yeah, the problem, ya Yaman, sometimes the object is not moving. So how to use the velocity to reach the center of mass? Sometimes the object is stationary and you need to calculate its center of mass. Yani you are an engineer, مثلا. You are an engineer and you design a piece of equipment. And in order to design it properly, you need to calculate its center of mass mathematically. So you can apply the laws of physics. So sometimes the material is not moving in a certain velocity, so still you can calculate the center of mass. Ahmed, I don't get why would objects move different distances if the whole object is pushed from the center of mass. Well, yeah, Ahmed, in real physics, look at this situation. Look at this situation. Yani, this is just for Ahmed. It's not. I will not ask you questions for that, but look at this situation. We have a spring, mass 2, mass 1, and here is the center of mass. Everything is moving. Center of mass, V center of mass is moving this direction, However, while the center of mass is moving from left to right, M2 is vibrating left to right, and M1 is vibrating left to right, while the whole object is moving from left to right. So it can happen. Well, if you don't have a spring, it's a very, very special case. You never teach the concept with a very, very special case. No, you teach the concept with a general case and then you go to a specific case. So the general case, M2 and M1 could have whatever motion, and yet the center of mass motion will be different than the motion of M2 and the motion of M1. Or you can have a motion of M3 and M4. You can have N particles moving at different, each particle will move with a different velocity in 3 dimensions, and yet the whole thing is moving as the center of mass is moving in another direction. So that's the general case. If they are attached with a rigid object, of course, that's a very, very specific situation. طيب. Yeah, look at a sample question in the book, because the time is very limited for me. If I go through all the examples in the book, as I told you before, each chapter will need 2 or 3 weeks. So look at the book, full of examples. If you have any question, come during the office hour. ما في مشكلة. إن شاء الله عبد الرحمن، حياك الله، أهلا وسهلا. طيب هلا let's look at a system. Let's look at a system of many particles. System of many particles. As I was explaining, not only 2 particles, it's a system of many particles. For that, I will do the derivation again with you. I'm repeating the book, but I will go step by step. Maybe it will make it clearer. Okay, so we start with the center of mass vector, and it is the total 1 over the total mass, and then I do summation of mi ri vector. طيب, suppose I derive the center of mass vector with respect with time. So I will just derive all the tiny vectors with respect to time. But what is this? What is dri over dt? Well, it is nothing but the velocity. So the derivative is the velocity. معناته I have V center of mass is equal to 1 over m, the summation, mi multiplied by the vector vi. So لاحظوا هون I have the center of mass a vector, and I have each the velocity vector of the center of mass, and I have the velocity vector for each particle. Now I have m here, That's correct. Yeah, Ahmed, yeah, Adil. Exactly. So now I have m here. So I want to get rid of this m. So I multiply both sides with m. So this is an m. This is an m. So then I will get m v center of mass, and this m disappear with this m. They cancel, and it is nothing but mi vi vector. طيب, I can derive v with respect to time. Yes, I can. Is equal to the acceleration. So I end up with center of mass is equal summation mi ai vector. But what is this? mi ai. It is the individual forces acting on this system, and I end up with this famous equation and we saw this equation many times. So, as I told you before, the concept of linear momentum is the father of Newton's second law and Newton's third law. Summation of forces, net summation of forces is equal ma. So the father is linear momentum. يعني we should it's another way of teaching Newton's second laws, and we start with the conservation of linear momentum, and from there we will reach to Newton's second law. And net force is equal mass multiplied by acceleration. Because in my opinion, linear of momentum, conservation of linear momentum is the big father, is the big grandfather. And from there you can get Newton's second law, and from there you can get the center of mass calculation. And of course, it's clear now that what you saw here is this one. Same result, but I know it's confusing, so I went step by step with you. So let me just, Khalid بقول attendance, let me just finish this, and by this we finish chapter 9. We come to the same result that we started with. When there is net external force is equal 0, then the change of momentum is equal 0. And if the net force is acting on a system, then we have delta P is equal to the impulse that we saw at the beginning of the class. So again, if the net force acting on a system is equal 0, momentum is conserved. If there is a net force acting on a system, then you have a change in momentum, and that change of momentum, we call it the impulse. We call it the impulse. And here we are not talking about one object, now we are talking about a system of objects moving together. A system of objects moving together. And like this, we end chapter 9. Let me stop the recording.